it is mostly useless, right? But just like what we have done in linear regressions, we start the linear models, right? So we start with the core tool, the linear regression thing. Then we talk about all kinds of generalizations, regularizations, and all kinds of small fix that solve some aspect of the issues. And today we're introducing the core tool in the second family, right? The tool itself is not going to be really helpful in practice, but next week we'll talk about the real things that are built on top of these conceptual tools, right? So the important thing is to understand this idea conceptually and to be able to kind of identify what are the good data for these kind of tools and what are the good data for linear kind of tools, right? And another nice thing for today is just like in the past we have been talking about regularization. We have all these different type of formulation. And today when we talk about trees, we would kind of go through the whole process we have been experiencing. We talk about the algorithm of building trees. That's exactly like the algorithm of finding the coefficients, the betas for linear regression or logistic regression. And we talk about how do we make sure these models not overfit. And we talk about regularization of trees, just exactly like the regularization of linear models. So pretty much all the major steps, there are kind of a one-to-one correspondence. So that also makes a good review, but we will run much faster. So today the whole session will just go through what we have done in the first four or five sessions, right? So that's a main thing. And next time we'll introduce the more kind of in terms of a prediction, the more useful stuff. Right? So that's the plan for today. We are going to introduce trees. We'll talk about, we start with regression, just like the linear regression model. Then later we'll talk about the classification. How do we use trees to do classification? That corresponds to the logistic regression stuff. Right? And in the middle, we'll talk about the process of building and pruning trees. So this is like finding the coefficients, the betas, and finding the regularization parameters, like in last, right? Building is the process of constructing the model. Then pruning, so this is a tree, right? Tree can kind of grows really quickly, and we want to make sure it doesn't overfit, so we would cut the trees, make it smaller. That's exactly like regularization. We don't want to have too many predictors in our model. We want to shrink that a little bit. Right? So that's a building process and a pruning process. So at the end, the more interesting thing is about the comparison between these two models. Let's see what are the strengths and what are the weaknesses about the tree families. Right? So that's the big plan. Okay, so the idea of the tree is kind of simple. So we want to group the data points according to their x, such that all the data points grouped in one group, they share some similarity in terms of their y. Therefore, once you have such a grouping mechanism, if you can group them together and cut the data set into multiple groups, within each group, they are very similar in their y. And that gives you a lot of information. And in the future, when you need to predict, you basically place that particular data point into a particular group. Right? If you are able to put that in a group, you know all these groups, they all have similar y's. So the prediction makes it pretty easy. Right? But that's the idea. We want to group the points based on their x. And the objective is we want to come up with the best way of grouping the points such that within each group, they are all very similar in terms of their y. Right? So that's the thing. But it's easy to talk about this idea, but the implementation is quite challenging, actually. And before you get into the algorithm, this whole thing would work for regression and classification. So the whole thing is about the similarity within the same group. Right? If the points are similar and either is a regression, you are predicting some numerical y, so you can predict based on the other group members based on their Y you can predict. Or if it's a classification, you can use the other group members 0 or 1 labels and use that. If the majority of your group mates are 1, then you predict this guy to be 1, right? So that's kind of the similar applications. So we kind of combine the two things into one framework. So let's have a quick example. This is the baseball data again. We talk about the baseball players, their salaries, and remember that we have one Y, that's the salary of the baseball player. So we were using this data set to predict using all the other 19 different X. Right? So here in this small example, we choose 2X. We just have 2 predictors so that we can visualize this whole thing. Right? And Y is the logarithm of the salary. So that's the target that we are interested in. Log is not necessary at all. Later we will see we don't really need to do nonlinear transformations in tree models. This is mostly for the sake of a visualization. Yeah, let's just think about this salary is Y, right? And then have I just randomly pick 2X. X1 is the years of experience playing baseball. X2 is hits. I forgot the details, but if you go back to the data set, it's about last year how many hits these players made, right? Some performance measures of the players, right? So, and each data point here on this predictor space. So this is the so-called predictor space. Right? Earlier we said we have 2-dimensional predictors, so this is the two-dimensional plane is predictor space, right? So the idea of trees is we want to group these points. Every point is one player. We want to group these points based on their Ys. Right? We want to say, hey, people with this kind of years of experience and this number of hits, they are similar in terms of their salary. Right? That's eventually the thing we want to say. So, so the Y is indicated by the colors. Right? So every point has a color. The darker, the cooler colors indicates a higher salary. Purple, blue are high salary. This is log of the salary, but that doesn't matter. The green, yellow, they are the middle salary, and the red, orange, they're the low salary. Right? So color indicates that. Right? So if we really have to group the points manually, how do we do that? So we basically need to generate a number of regions in this space, right? How do we group them? Okay, so we put some cuts here, right? And what's the message? Everything, the cut would split your space into two halves, right? The upper right half are the mostly blue guys, right? So they are the highly paid people, right? The lower left, they're the lower paid people, right? So that's basically we have split the whole space into 2 groups already, right? But tree method says you can split that into multiple groups. You don't have to stop here, right? You can split further, right? So we have further splits. How do we do this? Maybe I want to separate the red, orange people with the green, yellow people, right? So you can keep splitting. There are 2 extreme guys, and who are these guys? No idea, but if you're interested, you can go back and check their names. But they seem like I have a very small number of experience. No performance in the past, but they're paid a lot of money, right? There's kind of the superstar, young star kind of thing, right? I guess, but maybe if you check their name, I don't know who's who. Yeah. Anyway, you can treat them as outliers if you believe there's some monotonic relationship, right? The more experience and the more hits, you should have a higher salary. right? You can treat these two guys as outliers. But anyway, they are different, right? So if you have to cut them, they should be separated, right? So there was one time we have a kind of such an analysis. We were trying to do that for the MBA program. So we collect the MBA students, their GPA when they were studying in the program, and also their salary after 3 years. So the salary is a Y, and the GPA was the X. So they were trying to justify the importance of studying. so they collected all these data and did a regression. It was upward, going up, right? So the higher the GPA, the higher the salary after 3 years. But that was mostly driven by two outliers. Like there were two extreme guys. They are having super high salary, somewhat kind of, and we went to have to check who are they. Turns out to be two kind of Saudi Arabia prince or something. Some people from the Middle East. They graduate, go back, and they have a super high salary. And if you take out those two guys, actually the slope is negative. Slightly negative. We used to show that in a statistics class. And that's a very bad signal for the students. But anyway. But anyway, that's a big major idea. Idea is to split the points into groups, right? The ultimate goal is they should be similar in their Y's. So here, when we're splitting, we're looking at their colors, right? That's their Y's, not other things. But after the splitting, we can make up the stories, like what are these people? These are the experienced and high-performing players. Right? So based on the split, we can go back and check the X. What are the common things for these players? What are the common things for these players? They are the young and inexperienced, not having very good performance. Right? So that's eventually the story. Right? But in general, to have arbitrary ways of splitting this predictor space is pretty hard. Especially if we want to model that mathematically, you can do anything, right? That's pretty hard. And the tree methods try to simplify this thing a little bit. It basically says if you want to split the data points further, you can only split either horizontally or vertically. So when you split, you have to split along one of the X, right? So this is too ideal. It's too complicated, right? Just to make the problem slightly simple, is we can only split things this way, this way, vertically or horizontally. Every time when you separate the points, you separate them based on one of the X, right? Like the first one I plot is to separating people based on their X1. Their X1 large or small, right? Small goes to one side, large goes to the other side, right? Then I split for some further things. So that's basically the idea of this tree. So I'm showing you the final outcome of running this tree method on the data. So the final outcome is a tree like that, right? So let's leave the tree building process on the side. Let's first have a look at the output and what are the information embedded in the output, right? Then we come back to talk about how this thing is obtained. Right? So this is a tree. This is an upside down tree. The root is on the top. The leaves are on the bottom. Right? So there's a root. And the first thing is you can, when we build this tree, the only thing we tell the software is we are having such an Y and such two X. Right? So that's a Y. This is my X1, X2. Right? So that's the formula we have done in regression. The same thing. And that's the only thing we need to specify. There's not much extra things. There's some tiny parameters later. We'll talk about that, but no major things. Right? And after the tree building process, we have a tree like this. Right? at the end we will see that in this tree there are several special things. There are two internal nodes. One guy is here, the other guy is here. This is the place where people are split into two groups, right? So you can think about putting everybody, all the data points on the root. Then everybody needs to go through the first splitting point. So this is it generates two different branches. And the splitting is based on one of the x. In this case, this is the final solution. Right? In this case, the first splitting is based on x1. It's based on a logical statement about x1. Whether these players have more or less than 4.5 years of experience. That's a simple condition. Everybody has a yes or no answer to that. So you can check their data points. And if the answer is yes, these people go to the left branch. If the answer is no, they go to the right branch. Right? It is just some convention. There's no particular meaning. But you're basically separating them into two. Right? And those who go to the left actually they have no further split, so they end up in one of the groups. We call that a leaf. So that's a terminal node. Terminal node is basically a leaf of the tree. So on this tree we have 3 leaves. Right? Let's leave the leaves for a while. Right? So those who go to the right, so those who don't have small experience, right? Those who have a lot of experience can be further split into another 2 groups based on x2. x2 is their performance, and if they have a bad performance, hits less than 117, they go left, otherwise they go right. Right? So at the end of the day, all the data points are allocated into these 3 groups, right? The 3 leaves. That's the tree structure, what it tells us. And on the 3 leaves, we have 3 numbers. Right? I'll talk about this. On the 3 leaves, there are 3 numbers, and these numbers are the mean, the y bar. Basically, this is y bar for those in group 1. This is y bar in group 2. This is y bar in group 3. Okay? So it basically says, after going through all this tree building process, the algorithm believes these players can only be split into 3. So that's the best possible way. So people who are in the same group are considered the same. So there's no further way to separate them. They're all similar. And if they're all similar, we need to say something about what's their y. And that's the average. Right? That's the average salary of people in the first group, basically the young players. Right? And then you have different average for the other 2 groups. And these numbers will be the prediction. If in the future you have a new player, you have to allocate that player to one of the groups. You say, yeah, I have another young player. According to his x1 and x2, this young player should go to group 1. And what's the best guess about this new young player's salary? The best guess is, since he's in this group, the average salary of people in this group is 5.11. So the best guess is 5.11. Right? There's no way to further differentiate. Right? This is a best guess because we're minimizing the squared error, all these things. So the best guess is the mean. Right? So later we will use these leaves, the numbers on the leaves for prediction. Right? But at this moment, these numbers basically indicate these people are the same because they all have salary around that number. Right? That's that. Okay. Any questions?
So how do you come up with a condition?
Yeah, we'll come back to the algorithm later. The algorithm, we need to search all the conditions. Do I split people by 4.5 or 4.6? Right? The algorithm will search. So these are the conditions are basically the betas we were searching for in linear regression. We need to find all these betas. Right? And it's not only the 4.5 value, right? It's also, do we split by years first or do we split by hits first? There are two different acts. Right? So all these are determined by the tree building process. Right? So, and once you have that final tree, you can map that information embedded in the tree to your original data space. So that basically says the tree basically represents these things. You have R1, R2, R3, and say this is split 1, split 2. So we have all these 5 different nodes, right? So that basically says, yeah, you have this bunch of points. The important thing is let's do that. So this is S1. The threshold is 4.5. Those who are on the left are the young guys. Those are on the right are the senior people. And among those, where's my mouse? Among those who are senior, there's a second split. So this is the second split. So this is 117.5. So this is S2. Right? And you can see this is vertical split and horizontal split. It's horizontal because we are separating people based on their hits. And people can only be up or higher or lower than the threshold. Right? So that's going to be a horizontal split. And that's it. That's the final solution. Yeah, you have a bunch of lower paid people, the red and yellow guys, and the blue and purple guys, and the green people, and they're nicely separated, right? It's definitely not the best way of splitting because we limit ourselves to vertical and horizontal, but that captures some information here, right? And yeah, you can further split if you want, but that may have some overfitting story. We'll come back to that later. So that's basically a subset of the information embedded in the trees. But we typically use the tree to describe everything. So that's everything we have found out at the end. That's our model. This picture only shows partially the information. There are a lot of things are missing on these trees. One is the sequence. Right? It's not like a linear regression. All the X showing up in your model are equivalent. There's no importance. But tree is a sequential process. Right? So clearly there's a sequence, and the sequence means something. Right? So he said years is the most important variable to draw the first split. Right? That's the best way to split the people into two groups is by years. Right? And then there's the second one. There's the sequence of that. Right? And the sequence is meaningful here. And another more important piece of information is you may wonder why we draw the tree this way. So the length of these branches also means something. And the length of this branch means the reduction in the errors. So let's think about this as the residual sum of squares. So that's a reduction of residual sum of square by splitting the big group into two. Right? Think about if you have the big, without that split, everybody is in the same group. And if there's only one leaf for that tree, your prediction for everybody's salary is the average of everybody. So that's a null model in linear regression. Right? And you will have an error somewhere. Right? Later when we do coding, you will see that. The null model has an error. Then by splitting people vertically into left and right, and people on the left, they have a mean. You can have an error for those guys. People on the right, this is a second group, they also have a mean, and they have an error. Right? Everybody has their true salary, and you can compare the true salary with the prediction. Right? You have another error. So the total error added up is smaller than the original null model because you're only doing that split because you can reduce your error. Right? And that length of that branch indicates how much error you are able to reduce. Right? So the absolute length doesn't mean anything. So this is relative. Right? You can see the first split always gives you the most amount of gains. This also by construction. We choose the first split to obtain the most benefit. Right? Then the follow-up benefit is going to be smaller and smaller and smaller. And you're going to have a lot of short branches later you will see. And that's because by further splitting these group into two, the marginal benefit is getting smaller and smaller. Okay? So that measures how much benefit you get. That's also an important piece of information. What else? Okay, that's pretty much it. All right, so that's the final tree. So we've been talking about once we get a tree, what are the informations we can get from that tree? Right? So the next question is, given this tree, what are the stories? How do we interpret this thing? How do we translate that tree into some insights? So this is one of the major things that makes tree popular, because you can make a lot of nice stories, right? You can think about a year is the first major split. It says that the important factor separates the high-paid and lower-paid players, right? And the more experience, the more salary, and 4.5 is the critical threshold, right? You have all these stories. Then given after the split, given the player has less experience, the hits no longer matters. They are more or less similar, right? Those people on the left group. But for the other side, people with experience, now hits becomes important. If they have more hits, they can get more salary. That's 7 point something versus 6 point something, right? And yeah, that's the story, right? So you can say all these things. This tends to be more intuitive than a linear regression model, right? When you have a linear regression, your story is like when the number of years increased by 1, the salary increased by 2.5, something like that, right? This is more intuitive, right? So, but later you will see this is one of the major benefits of using trees will be destroyed by some of the negative things. This doesn't exist. The benefit doesn't exist in practice. So, but at this moment, at least, given a tree, you can say something. And yeah, and we have briefly talk about given a tree, how do we do prediction, right? So we just whenever there's new data points, we just ask these new data points going through the trees, right? Are you satisfying the first condition? Are you satisfying the second condition? At the end of the day, all the new points end up in one of the groups, and if you are here, then the prediction about your salary is 6. Right? There's nothing more than that. That's the only information. Right? That is not a nice thing, right? You can imagine if you have 10,000 players to predict, and all these 10,000 players will pick one of the 3 numbers. There are only 3 different values for prediction. Right? So in general, trees are really bad at coming up with accurate prediction because it doesn't differentiate individuals very much. Right? That's the issue. So yeah, that's I have described. Basically, place people into the groups, and once you're in the group, you can just take the average. All right. So that's about having a tree. What are the message we can read out of a tree, and how do we use that thing for prediction? Right? And let's get to the core stuff. How the tree was built at the very first hand. So the building process can be framed like an optimization problem. Just like in linear regression, we talk about these things, but at the end of the day, you need to find a line. So in order to find a line, you're choosing your coefficient betas to minimize the residual sum of square. Right? So here is pretty much the same thing. We are basically choosing the regions or the groups to minimize the residual sum of squares. Right? So you can write it like this. So that's the total error we want to minimize. Right? This total error can be split into several components. First, you can think about this is looping over all the groups, I would eventually have J groups. J is a decision. It's not a determinant at the very beginning. But eventually, I'll have J groups. So I have sum over all J groups. Right? That's a total error. It's the sum of the errors in each of the group J. Okay? So that's the first level of sum. Then inside the sum is the error of group J. Right? So this is the error of group J, small j. Right? Can be any group. What is the error of group J? You say in group J there are a bunch of points, so we need to sum over the error of every point in that group. Then how many points are there? So that's all the points that are in group J, allocated to group J. So we sum over all the points. For each point, they have their true y value, and they have their predicted value. And the predicted value is simply the average of that group. Right? So that is the average of y in group J. Right? So if you allocate these points in the same group, and their prediction, even this is in sample, but their prediction is the average, right, of everybody. Then everybody minus their average is their error. So we take a squared error. So that's we take a squared error. That's the error for a particular point. We sum over all the points. So that's the error for a particular group. And we sum over all the groups. So that's total error, right? And that's the objective, right? It's not fundamentally different from the linear regression objective, right? But the issue is how do you find all these R thing, right? So given a kind of allocation or grouping scheme, I can measure the error easily. But how do I choose the optimal way of doing this, right? That's not trivial, right? Actually, it's not beyond not trivial. It's actually not feasible. In general, there's no way to solve this optimization. Right? So we just at the very beginning we just said these can be arbitrarily defined regions. In trees, we use rectangles to simplify the problem. But the problem definition didn't require the RJs, the regions, to be rectangles. You can do ellipsoids or any other shape, right? So if you can solve that optimization, of course, you can do whatever. But the issue is even rectangles we cannot solve, right? So the problem we have seen is easy because it's two-dimensional, right? If you have a 20-dimensional, how do you define a square region in a 20-dimensional space? You need to all these kind of constraints, right? That's not easy. So anyway, that's the major difference between trees and linear models is the optimization is not solvable. There's no straightforward way to get the best way of separating the points. Okay. So it's hard. It's hard, and in general, no solution. So there are a bunch of famous algorithms to approximate, give you some feasible solution. That's not the best possible one, but gives you a sort of a good enough one. Right? So that's the idea. There are a bunch of algorithms, and today we're going to introduce the most classic CART algorithm, the classification and regression tree. Right? The algorithm is not particularly special, but just to highlight the problem and the algorithm can be separate. Right? You can still have the same kind of problem and use whatever algorithm to. There are a bunch of other algorithms to group the points. Right? But the simplest possible one is this guy. If you think about that, this is essentially the forward stepwise model selection in linear regression. That's exactly the same problem. In linear regression, before we have the tool on Lasso, we are facing the subset selection problem. We need to choose which X to be in the model, which shouldn't be. And there are all this number of combinations Right? That's also, in general, not solvable problem. Right? So people say, what do? We find some simple shortcut. We do forward stepwise. Choose the best x first. Choose one x first, add to the model, then keep that there, choose another one. Right? So this is essentially the same thing. I don't know what's the best way of cutting this whole high-dimensional space, but what I know is if you ask me to cut it once, I can probably find the best place to cut. Right? So I just myopically choose, if I'm just cutting that space into two, what's the best way of doing that? Then I have that. Then I think about next step, what do I do? I still need to choose an x to split again. Right? So every step is about myopically choosing, just thinking about I'm just doing it for once. I don't think about the future. I may just get into trouble. Right? So if you don't think about the future, this is not trivial, but at least feasible. That's at least feasible. Right? So the sequence, because it's forward, it starts with everybody as on the root. Right? Think about now we need to split into two. What's the best variable? The decision is more than what's the best variable. Given you choose a variable, where to split, right? What should be the threshold? Then you sequentially continue this whole process. Okay? And every time you split, you are adding one extra leaf, right? You start with one leaf, everybody is there. You have a split between two. Then you choose another leaf to further split that, it becomes three. So every stage, you're adding one leaf to this problem. So a quick simplified view of the algorithm, right? So this is where we start with a whole leaf with everybody in there. So the first question is really, do we split along x1 or do we split along x2? We have that. We need to choose, right? If we split along x1, there are multiple things about what should be the threshold. If I want to cut along this number of years, what should be the threshold? There are infinite number of points I can choose what should be the best one. Or if I choose along x2, what should be the threshold, right? So I have infinite number of candidates. I need to choose the best one, right? The best one such that after splitting, I'm minimizing the resulted error, right? This is not the extremely hard type of problem. So in mathematics, there are different types of hard problem. This is not hard in the sense that if you give me a split, I can tell you how much is your error. That's pretty easy. Yeah? If I have cut this, I can easily calculate the mean in the first group, mean in the second group, and tell you the error. So evaluating one policy is in general trivial. But how to find the optimal one is difficult. So that's a middle level hard mathematical problem. The harder one is, even if I give you a policy, you don't know how to evaluate them. You don't know how good it is, right? That's even harder. But this is still fine. So the algorithm is basically comparing between the two. Cut along x1 or along x2. And if I have to cut along x1, I need to choose the threshold. And that optimization is easy. If I have to choose one place to split these two group points, this is relative to all the other steps, this is easy. Okay? So at the end of the day, you compare all these possibilities, and so that's a solution. Right? We find, if we have to do that once, we just cut along years 4.5 or less than 4.5 or larger than 4.5. So that's the first split. So we are only growing the tree by one extra layer, right? And the next layer, the problem getting bigger and bigger, because now you have two leaves. So the first thing you need to decide is, do we cut along your leaf 1 or do we cut your leaf 2? You cannot cut both leaves, right? At one time, you cut one of the leaves, right? If you cut, this is R1, this is R2. right? If you want to do epsilon R1, then you face the same decision, x1 or x2. x1 or x2. Then you still need to think about the threshold, the different threshold, right?
Why does it matter which one you pick to cut? Because you're looking at different subsets. So you could cut subset R1 or subset R2, and it doesn't affect the other one.
Yeah, but you imagine you can only cut this once. So the constraint is I only have one extra cut. So do we introduce a split here, or do we introduce a split here? Which one is better? That's my question.
Okay,
so
you're limiting yourself to only ever being able to add one more cut.
Yeah, you don't think about in the future what you can do. If you have to think about the future, the problem becomes much bigger. You can say, I don't cut it now, I can leave that to the future. And the future, there's too many possibilities. Even the myopic version, there are already a lot of kind of options there, right? Yeah. No, so even if you believe you should cut throughout, it's basically two extra cuts. You split the group 1 and split the group 2. So you can leave one to the future. Right? So this doesn't rule out in the future you cannot cut again, right? That doesn't rule out anything. But now you just say, I have these two leaves. I need to choose one to split them into two, right? So that's the next level of decision. Now we are only having two leaves. We are getting a much bigger problem. And we need to choose one of the leaves to cut. And we end up, the answer is like somewhere here, right? So that's the best one chosen by the algorithm. So that's not that crazy, but it just the problem size will go up, right? Now you have two leaves. Next one you have three leaves. Then you need to choose among three. Then you can have 200 leaves. You need to choose among all these things. And also here the dimensionality, the feature space is only two-dimensional. Right? You can have 1,000-dimensional then. You need to choose one out of 1,000. Right? So computationally, that's not as nice as linear models. Right? So there's something we are going to lose. And the question is, the next question is, if you can just keep splitting your points, if the algorithm is not a headache, you can just split as you wish, when to stop? Right? That's the next question. Or do we ever need to stop? Right? Can you imagine if just keep splitting what's going on? Yeah, so every point becomes one individual leaf, right? What's that situation? Have we seen this kind of situation? There's a k-nearest neighbor with one neighbor, right? So you are in that group alone, and the prediction about yourself is yourself, right? So because you are the mean of that group. So you get a perfect tree with no in-sample error, right? That's a k-nearest neighbor with one neighbor, right? And that's clearly going to be an overfitting situation. Right? So we cannot just have an arbitrarily large tree. Otherwise, that's too simple. Right? Every point is one region that we don't need a tree. Right? So clearly, that's not going to be the best thing to do. So we need to think about when to stop. Right? That's the next question. When to stop doing this? How big the tree should be? Or in other words, how many groups or how many leaves should there be? Right? This is just like the lasso kind of thing. How many predictors you want to include in your model, right? If you include too many, you're overfitting. And the quick answer to that question is you need to do cross-validation to choose the right size of the tree, right? But let's not get there yet. But there's some technical challenges, so we have to first get a big tree without really thinking about overfitting. So in general, the software packages all have some stopping criteria. There are three in the package we're using. There's a mean cut. Oops, what's this? Mean cut. So you can basically specify these conditions such that whenever these condition, any of this condition is satisfied, we stop further splitting, right? So the most straightforward condition is mean size. If the leaf only have like 10 points in there, we can no longer split that further. We want to make sure it's no smaller than 10, right? So this is a minimum size. You want to make sure your leaves is above the minimum before you're further splitting that. Alternatively, you can also think about the gain in terms of the length of the branch, right? You say, if I split that further, is the gain large enough to justify this split? Right? So that's the minimum deviance. Later we'll come back to the deviance is the same as the residual sum of square in regression problem, right? So we say, if we split, we need to make sure the gain is at least that big, right? Otherwise, we don't do that further. And then there's a mean cut. Mean cut is somewhat similar to mean size in that sense. So mean size sets a constraint on the parent node. You have a node, the parent. If the node is too small, you cannot have children. That's the story. The parent must be big enough. The mean cut says even the parent is big enough, and you are allowed to further split the parent, and the resulted two children may not be symmetric. You may have one children with 1 point, the other children with a lot of points. Right? That's also not allowed. So you can set a constraint on mean cut. Mean cut says the resulted two children should have at least these many points. Right? But these are all pretty arbitrary and really data dependent. Right? There's no clear way to say what is the best number. Right? Pretty arbitrary. But these are the options that are controlling the size of the trees. Right? If you have a very loose constraint on that, your tree will just go really kind of a bushy trees. Okay? Yeah.
Just wondering, for this population, can we cut that diagonal or?
No. Even this is already not tractable. So there are all kinds of attempts to improve on that. But the issue is at the end of the day, you have these many leaves. And these many leaves, when you use those leaves to do prediction, that's not going to be accurate anyway. So I just choose to skip all this improvement. Next week, we'll talk about the super smart improvement built on top of that, solved all the problem. Right? So now let's try to understand the core thing. But keep in mind, this is a bad thing, a bad tool as itself. Let's not bother make a better version of that. Yeah. Okay. So at the end of the day, this tree is the final tree if we just implement the tree building process, what we have described on the data. So that's not what we have seen at the very beginning. What we have seen is a smaller tree with 3 leaves. Right? But this is the first half of the algorithm. We just keep splitting until we reach some of the stopping criteria. Then we just stop like that. Right? This is a pretty crazy tree with 8 leaves. Right? This is 8 leaves using the default stopping criterion. So 1, 2, 3, 4, 5, 6, 7, 8. What are the observations? One thing I want to highlight is these 2 guys. So you can see that there was a one split. You were cutting the people according to their hits above or below 114, right? And the next one, you have another cut that is again along hits above or below 40, right? So that's essentially this is one of the subgroup. You cut it here, then next one you cut it here, right? So that's essentially a 3. It's not a binary tree. It's basically cut the space into 3 groups. right? So sometimes people really worry about why we are having this binary tree every time we are just splitting in two. If we can split, and if at every iteration we can split that into 3, can we make a better model, right? But it doesn't stop you doing that. So having 3 splits is basically do that twice, right? You can always capture that if necessary. Right? So yeah. What else? And this is a simple problem with only 2x, right? But sometimes you use x1, sometimes you use x2, sometimes you use x2 again, right? And even when there's only 1x, later we have an example with only 1x, it still does the same thing, right? But cut x here, cut x here, right? It doesn't matter, right? But when you have many x, then some of the x may not show up in the tree at all. Actually, there was some information about which variables actually show up in the trees. Right? There are some insignificant ones that didn't play any role. Right? Okay, and the final tree, it's not the final tree. This is after the tree building process, you get a massive tree, and the massive tree can be mapped to your original predictor space. When it's 2-dimensional, it's going to be something like that, right? Some rectangular, vertical, horizontal, right? So the point of this slide is you can never have something like that, right? Every region must be a perfect rectangle, right? Yeah. So whenever you cut it vertically or horizontally, you cut through the whole subgroup, right? You don't stop in the middle, all those things. Mm-hmm. And that's the final model. Not final model. According to the tree, that's how we visualize that model, right? So we have an x1, x2, and we plot this y hat, right? So any data point, any new or existing data point will eventually belong to one of the 5 regions. So in this problem, you have 5 regions. There are 5 terraces here, right? So every region is a nice rectangle, and the height of these regions is the mean of the y's for those points, right? So if you visualize, that's the prediction, right? Give me any data point, I'll put it somewhere. I check the x1 and x2, I'll put that point somewhere, and once I know the location, I know which group it belongs to. If I know which group it belongs to, I can check the average of that group. That's going to be the prediction. Right? So that the picture shows, like, by using this tree, at the end of the day, you have a kind of a massive step function. Right? How many steps is really how many leaves you have in your tree. Right? And this thing is nice in the sense that it can capture the nonlinear shape in your true f function. Right? So think about your true f is a bell curve, something like that. You can always use multiple steps to approximate that. Right? But if you're using linear regression, you get a flat line, not flat, flat plane. Right? You'll never be able to capture that unless you introduce the polynomial stuff. Right? Later you will see this. The best point of trees is to capture the nonlinearity. Right? If there's an ugly shape, it can always come up with many tiny leaves, give you many tiny steps to approximate those things. Right? Okay? Okay. But that's that's not very granular, right? That's not going to be smooth, not very going to be granular. You only have 5 groups, so you have 5 steps, right? But it capture the pattern. Okay, that's the first step, growing a massive big tree until we reach the terminating conditions. And then the next question is, we know we are building a big tree. All these trees are subject to overfitting because we are building a lot of leaves. And the next question is, how do we kind of contain that tree and make sure it doesn't go crazy? Right? This is exactly the same idea like regularization we have done. We want to limits the flexibility of this model, right? So what measures the flexibility of this model? Which number tells you how complicated, how flexible is this number? The leaves, right? Number of leaves. So we want to, just exactly like the best subset selection, we are controlling the number of predictors in the linear model. Here we are controlling the number of leaves we want. So we have assign a penalty. Right? So that's exactly the same idea. So we say, now we need to worry about overfitting. We can build a big tree, but that's dangerous because of overfitting. And to the extreme, if we build a massive tree, everybody is in a leaf, then we have 0 in sample error, but out of sample, that's going to be bad, right? So we have to control the tree. And in these trees, the major flexibility is how bushy is the tree, how many leaves are there, right? A tree with 3 leaves versus a tree with 300 leaves, they're different. So we want to control this number of leaves. And to control that thing, we would do regularization. And this is just like the subset selection, but coming from backward. Because we already have a big tree. What we need to determine is, hey, some of the branches are not necessary. Let's cut that branch and shrink those multiple leaves back to a big group. Right? So that's the idea. So that's like the backward selection. The corresponding thing in linear regression is you start with a full model with all the predictors in your model. Then you go back, you say, I need to take out one of the predictors. Which one to take out? And how to do that. Right? This is the same thing. I start with a tree with 8 leaves. I say, what if I'm cutting that to 7? What's the best way to cut? And if I cut that, what's the out-of-sample performance? Right? We will do cross-validation. So that's the whole process. We'll build a big tree with many leaves using the terminating conditions. And somehow we want to make sure that tree is in an overfit region so that we can shrink that back. Right? If the tree we built at the very beginning is not rich enough, then it makes no sense to shrink. Right? So we start with a big tree, then we prune it backward, right? Just like a backward model selection. When we prune it, we need to determine how small the tree we want, right? And that's controlled by tree size. Where's tree size? Tree size T, okay? And the way we prune that is exactly like the best subset selection. We have the residual sum of square. That's an in-sample error. And we want to, on top of the in-sample error, we want to have a penalty term. Alpha is the lambda thing we have in regularization. And here we are not penalizing on the beta coefficient. We are penalizing on the tree size. So this is the number of leaves, right? The cardinality of the tree, the number of leaves. Right? So absolute value of t, that's just like the number of predictors. So this is the number of leaves. Right? And this is not very intuitive. We said this is algorithm friendly, but not human friendly. Human friendly version, the equivalent version is the other one. I should have a minimum here. They're equivalent, right? Just like what we have seen in regularization. We can minimize the in-sample error, but subject to a budget. Our budget is this. I only have 5 leaves for you to do that. Right? You can only do 5 leaves. What's the best tree you can come up with? Right? So all these things corresponds to what we have done. Right? So that makes things easier. And what's the optimal budget for us? Or alternatively, what's the optimal alpha or lambda? So we need to do cross-validation, right? only by cross-validation we can tell this is the optimal size of the tree that minimizes the cross-validation error. Okay? And later you will see we don't really work with alpha, so don't think in terms of alpha. So optimal. Think about tree size. Tree size is much intuitive. This is more or less because tree size is a discrete. If we start with a tree with 8 leaves, when we want to prune, we have 7, 6, 5, all the way to 1, right? We only have a finite set of possibilities. Thinking about in terms of alpha is not straightforward. There's so many possible alphas, right? But mathematically, they're the same. So we can use cross-validation to find our optimal tree, and we can prune our tree, okay? Make it shrink it a little bit. So, and here is the final algorithm. Yes. Let me go through the algorithm, and we'll come back to the difference. So first thing, we build a big massive tree. Use the terminating condition. Right? Want to make sure that tree captures a lot of information. A little bit of overfitting is okay. Then we run the cross-validation process. This is just like the regularization. The whole point of this process is to find the best tree size. Right? Let's forget about alpha. Tree size is our parameter. We try different tree size. We use cross-validation to compare if we shrink that tree by 1, by 2, by 3, what's the cross-validation error, right? We can find the best tree size. Once we have the best tree size, we can do a final prune on our original big tree. And that's the standard workflow for trees. Is this clear? So the pruning process also needs an algorithm because you really need to think about, now I have 8 leaves. I need to choose one to get rid of. Which one do I do? Right? Let me go back to this tree. Think about this tree. I have 5 leaves. Now I want to get rid of 1. So there are several easier situations and several difficult situations. The easier situation is like you want to get rid of R1. That's easy. You just combine R1 and R2. Right? You're basically cutting this branch. Right? So I don't really need this branch. I just need a leaf all the way here. Right? I'm merging R1 and R2. That's okay. Or you can get rid of R4 or R5. That's the same thing. I'm cutting this branch. I just need a leaf there. Right? That's also easy. What about R3? Because at the time of pruning, you have to go through all the possibilities. Right? The other 4 are easy. But what if I want to get rid of R3? What happens? Intuitively, what happens? So you need to, there are some points, you need to put these points over here, right? So if that branch no longer exists, those who used to go left here cannot go left. They have to go right. If they go right, and they need to be allocated to R4 and R5, right? So that's a point. And that's the whole point of going all the way forward, get a big tree, then shrink it back. Right? You might find it strange. Why not just say, I find the optimal tree size is 3. Why not just grow a tree with 3 leaves from scratch? Why do you go all the way out and shrink it back? Right? That's kind of strange. This is part of the algorithm. There's no strong theoretical reason, but it's mainly driven by the issue that we cannot solve that optimization optimally. Even I know I can have 3 leaves. I don't know what's the best way to come up with 3 leaves. All the algorithm we're thinking about, if I'm doing ones, how to do that. Now you tell me I can cut it 3 times, find the best combination of 3 cuts. I don't know how to do that, right? So that's one part of the concern. And so all that we can do is going forward, cut that one by one. We can do that 3 times. We get a tree with 3 leaves. But that's not satisfactory because this is a myopic way of generating trees. And this is forward selection. Remember when we talk about forward selection, you say the first time you choose one of the X in your model, if in the future you kind of realize you were wrong, there's no way to go back, right? So you have to live with your earlier mistake and have further splits. So that's one of the issue. And the whole point of doing backward, grow a big tree and cut it backward, is to get rid of those potential regrets. So you might, at this stage of splitting leaf 4 and 5, you might already regret, I shouldn't have leaf 3 out there. But because you are doing forward, there's nothing you can do, right? And the idea here is, after having this big tree, we can go backward. And go backward, we can fix some of the regret. At least we can think about, if I want to get rid of R3 and reallocate these guys to the other leaves, that becomes a possibility, right? So going forward and backwards gives you more flexibility in that sense to fix your errors. It's somewhat like the step AIC. You can go forward, backward, and go both directions. That's something like that. Right? But yeah, that's very very heuristic kind of a way of doing things. Right? But empirically, that's better than just doing forward. Right? All right. So I have explained that already. So that's the major difference between best subset selection in linear models. Because in linear models, you can find the best ones easily. You can solve the problem easily. Here, you have to rely on the forward and backward and allow yourself to go back and forth to fix some mistakes. And yeah, once you have the pruning mechanism, you can do cross-validation, and this is a picture showing cross-validation. We start, why this is a 10? I don't remember. It should be 8. So remember, this is still the baseball data, and the big tree actually has 8 leaves. So the maximum should be 8. I don't know why. Maybe there's a different run. But your question is, starting from the full tree, I need to shrink it back. Right? I have all these alternatives. I can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? All these are possibilities. I have a mechanism to shrink back to that size. Right? So I know what should be those trees. So I can compare them in cross-validation. Which one? This is the CV error, the green one. So in terms of CV error, 3 is the best. So that's the optimal tree size in terms of this the best tree, minimize the out-of-sample error. Right? So I have the test error, just illustration, and also the in-sample error. In-sample error is always going down. Right? That's just like everywhere. Whenever you're increasing the size of your tree, you're improving over your in-sample error. So that gives us a mechanism to choose the optimal tree size. And once we have 3, we can go back and prune it again with all the data. Earlier, the pruning was based on cross-validation, right? Not very kind of efficient. So we will prune it again using our full data set. So we get optimal 3.
Is there a reason why the test error is so much lower?
I don't know. That you mean the test error, the difference between CV error and test error? That's all possible, right? That's yeah. The test data may not be a big data set anyway, so the test data also fluctuating a lot. Right? I guess probably when getting this picture, we were splitting the data into training and test. So there's a small test data on the side. That's why the trees is slightly different. So I guess I don't remember exactly. But later when we have an illustration, we'll do exactly the same thing. Right? Okay. So that's the pruning process. We start with a massive tree in the tree building process. After cross-validation, we realize we should only have 3 leaves. Now we need to prune it back to get our 3 leaves. And the result of the pruning was like that. Right? The result of the pruning. So that's the ultimate tree model for that data we have seen at the very beginning. Right? Complete the whole process.
So original size of the tree, for example, 8 here, right? Is defined by us.
Yes, defined by those terminating conditions. And I think when doing this, I was lazy. I didn't change the terminating conditions, so used default. Default is like the minimum group size is 10 or 5, something like that. But those are really arbitrary. I think in general you should try to change that. At least try to make sure the first tree you build is in the overfitting range. Because there are situations you have this tree, you run all this pruning process, you realize the optimal size is 8. So you don't need to prune. That's underfitting probably, and you need to go back and make it bigger, right? Change the coefficient. But most of the time, using the default, you will get an overfitting tree. Most of the pruned tree are like that. Most of the time. Yeah. Okay. So far, this is about the easiest context. We're doing numerical y, so this is a regression problem. We are having only 2x, and both are numerical. Right? And there are a lot of other challenges, just like after doing linear regression, we need to talk about logistic regression. So we need to talk about what if the y's are categorical? What if we need to do classification? So the prediction part, so given a tree, prediction part is not that difficult. Right? So you still allocate the points into the groups. And when you need to predict, you either take the probability. Right? So the idea is in your group, there are 10 points. Out of 10 points, 7 are 1s, 3 are zeros. So your probability of being 1 will be 70%. So that will be your probability. Right? Or if you really have to assign a label, that will be 1. That's the majority. Or you can think about this essentially using 0.5 as the cutoff. If the majority is always above 0.5, right? You're taking the label of the majority. Right? So that's not extremely difficult. Most of the time, what we do is we pull out the probability. Right? Whenever we're doing predictions about classification problem, say for each of the data points, what's the group he's in? And what's the corresponding ratio of 1s and zeros in that group? Right? That makes the probability estimate. That's the straightforward part. And the challenge is really how do we split the tree? Right? So that goes back to the same question when we move from linear regression to logistic regression. We can no longer measure the residual sum square. That's no longer a good objective. So we switch to deviance. Right? So we just use deviance. So the natural choice here is deviance. Where's deviance? Yeah, that's deviance. And actually, that's the best choice anyway. But there was an interesting question we never asked ourselves. Like when we were doing logistic regression, we never thought about, is deviance the only thing we can have, or are there any other possibilities? And here, people raised the similar question. When splitting these two groups, we can use deviance for sure. But how about classification error? Right? So think about earlier, we were splitting by years. Suppose the y's are 0 and 1. Right? So we can move that threshold left and right. If you move it a little bit, some people who used to be in the right group now move to the left group because you changed the threshold, right? And once they change, the prediction about these two groups becomes different because the labels of these groups are the majority labels, right? If the majority here was 0, majority here was 1. By changing that, you might change the labels in some sense, right? So once you change the labels, your errors will be different, right? So you can say, I want to choose the threshold that minimize the error, right? That's a possible criteria out there. But there was in the reference book, there was an illustration, like kind of a tiny example, showing that this is a bad choice because when you are choosing your threshold to cut, the misclassification error is really insensitive to the changes because it's all possible, like you're moving around, it doesn't change the labels of the two groups. Everybody is still labeled as 1 here, still 0 here, right? So it's very hard to find the optimal because that's not very sensitive. Just like your homework last week, when you are doing regularization for a logistic regression, when you're changing your lambda, the misclassification error is not very sensitive, right? For all different lambdas, they're all similar. Right? But if you switch to deviance, you get a nice, beautiful curve. You can immediately spot the optimal lambda there. Right? That's the same story here. So in general, but just the first level of message is whenever you're doing classification, there always this kind of struggle. Shall I use misclassification error or shall I use deviance? Shall I use something different? There are multiple things. For regression, you don't have that worry. Mean squared error is everywhere. You just do that throughout. But the next message here, at a stage of splitting the trees, building the trees, growing the trees, deviance is much better. It finds a nice threshold because it's more sensitive. It's very smooth. Yeah. And there's an alternative called the Gini index. So Gini index measures the equality within that group, right? Within that group, how many are zeros, how many are ones? If they are 50-50, this is super unequal. So there are a bunch of rich guys and a bunch of poor, half of the rich guys, half of the poor guys. That's unequal, right? If it's 99% rich guys and 1% poor guys, that's more equal in that sense. Yeah? So Gini index measures something similar. So, but at the end of the day, if you try, you see deviance and Gini index, they don't differ that much. So it doesn't make sense to struggle between the two. Just use deviance, it's good enough. So Gini index is a possibility in the R package. So you can choose that and see the difference. Yeah. But this is the tree building process. When you are deciding the threshold to cut your data points, deviance is important. And then, but when doing pruning, when optimizing and the tree size, doing cross-validation, when you're choosing tree size, the cross-validation error, in general, people use classification error. You can also put the deviance there, but there's nothing wrong. This is at the CV part. This corresponds to the exactly in your homework when you do lasso, when you choose the optimal lambda, you use the misclassification error. It is the norm, but personally I don't see a strong kind of support for that. I see they're all pretty much the same. See, if you use classification error, you basically assume the cutoff to be 50-50. That's a big assumption anyway, right? So yeah. Quick summary is at the tree building process, we for sure use deviance or Gini index, not classification error. But on the pruning process, there are multiple choices, and there's no clear agreement what to do, what's the best thing to do. Right? There's no clear agreement. Actually, later you will see in the software package, you can choose classification error. You can also specify the cost related to the false positive, false negative. If you have those information, you can specify that. Basically, you can specify the cutoff point. Right? There's a place to specify that. And if you don't specify that, they just assume 50-50. Right? And that's about classification when your y variable is categorical, a binary categorical. Right? The standard tree package doesn't solve the multinomial classification. If it's more than 2 categories, it doesn't work. You need some extra things. And the next struggle is about categorical X. If you have some predictors in categorical. So we haven't done that earlier because the 2X we had was numerical. Right? So now think about we have a categorical X. Right? Your homework data set, hot data. I don't remember exactly what was that categorical variable. But now think about you have a bunch of data points. You need to split them according to one of the categorical variables. Think about there are 3 colors, right? Red, green, blue. Right? There are 3 colors, 3 categories. So you need to allocate some points having color red, some points having color green. Right? So you need to basically allocate them to the left branch or right branch. Right? That's basically. In numerical X, it's easy. You find a threshold that naturally becomes 2 groups. But the categorical, there's no such thing, right? Red, green, blue. How do you decide? So that problem becomes more challenging in the sense that you really have to decide if these guys are red, do they go left and right? And if they are green, do they go left and right? If they are blue, do they go left and right? And you need to choose all these things simultaneously such that the error is minimized. Right? That's a challenging thing relative to finding a threshold left and right. That's more challenging. And think about for each color, you need to decide left and right. Right? So that's 2 by 2 by 2. You have 8 possible combinations. Right? You can have all these possibilities. And that's only 3 categories. When you have 32 categories, think about the possibilities. That's just exploding. So in the old days, all the decision tree software has a limit. The categorical variables have like at most 32 categories. More than 32, it doesn't handle that. Now I think they took it out or make it 64 or something like that. You have more powerful computers, you can handle bigger ones. But that's still a challenging decisions. So there's some heuristics or some algorithm to improve on that. Let's not worry about that. Yeah. But just keep in mind, whenever you have big categorical variables, that's a killer for the performance of this thing. Both here and the next time when we talk about the more advanced tools, it's going to be a killer, performance killer. Yeah. And the people defending decision trees said, in practice, you don't need a categorical variable with more than 32 categories. You should find a way to shrink. Yeah. If you have that variable, that means you didn't understand your data very well. There are a lot of practical workaround. 1 year we have a test data set that has like 100 different categories. At a basketball, did you see the basketball data set? NBA? No. Okay. So there is an NBA data set about player. They have different shots. You can have a slam dunk. You have 3-pointers. All these things. There are like more than 100 different types of shots. They can code that, and we need to do a classification on that. Which type of shot is more likely to go in, which is less likely, and all the tree methods kind of break down because of that 100 categories. So you have to group the categories a little bit. So the standard, the simple workaround is just keep the major categories, those with a lot of data, like Slam Dunk has a lot of data, and 3-pointers has a lot of data. But the majority of the categories don't have many data, so we just delete all the majorities, those smaller categories, call them others. Just relabel everybody as others. So you don't eventually have like 10 different categories. Okay? That's because of the technical constraints. Right? Okay, what time is it? All right, I have several extra slides talking about high-level information. Right? So if you think about the comparison between trees and linear models are stronger when the data is linear. Right? So here is a exaggerated example. So you have a 2-dimensional space. All the ones are here, all the zeros are here, and there's a clearly linear boundary out there, right? Then you can easily run a logistic regression. You can split the data into 2 perfectly, right? But if you have that kind of data, you run trees. The tree needs to approximate that linear boundary with step functions. So this is what you're going to have, right? That's not going to be very accurate, no matter what you try, right? So that's a problem. If the data is naturally linear, tree won't be a good solution. And if the data is naturally nonlinear, this is again a super exaggerated version. Tree will give you a perfect fit. Right? So these are the zeros, these are the ones. Right? Tree will give you a perfect fit, but lines won't do any better. Right? So in general, that's kind of the main thing. Is your data more linear or more nonlinear? If you cannot make the judgment, just run a horse race. Just compare the 2 anyway. Right? You will see. Yeah, it's not a big issue. So this is the again on the capturing the nonlinearity. Right? So this is the sine curve we have seen last time, probably. Right? So that's a true F in the population, the black smooth curve. And we have 100 data points from that population. That's a black curve plus some noise. Right? If you remember last time, if we run a linear regression, we'll get a line like that. Right? That won't be a good fit until you introduce the polynomial things, high order stuff. But if you don't, that's the best you can get. But if you just take that data, fit a tree, you get a nice and easy solution. That's nice. It used like 7 steps to approximate this sine curve. Right? It should be 7. Later we'll do that. So it's cut your predictor space into R1, R2, R3, R4, R5, R7. Right? So it grow a tree with 7 leaves. Right? All these vertical points are just splits. And within each leaf, you have a flat line that's the prediction. Right? So that you don't need to do anything. It's just automatically capture that nonlinear pattern. You don't need to introduce polynomial things. Right? Okay? So that's pretty much the only important slide for today's class. Right? So what are the good things and bad things about trees? We have seen some of the good things. I have the first set of the good things, and they're not really the good things. Easy to explain, easy to visualize, easy to interpret, works naturally with classification and regression. So these are, later we'll see they don't really matter too much. But the real important things, right? The real thing that kind of drives people to use trees are these. We have seen that it easily captures the nonlinear effect, right? If you have a sign, any ugly shape, it will be able to approximate that with a step function, right? And you can get a perfect approximation by introducing a lot of steps, right? You get a zigzag line, but you can get all these things. Right? It handles categorical predictors natively. So you have colors, you split the colors to left and right. You don't need the dummy variables, right? There's no dummy variables anymore. You just one variable. You just decide which category go left, which category go right. Native. In linear regression, what we really do is to convert categorical variables into numerical, although they're only 0, 1, but that's what we read, right? And there are no more interactions. That's a big thing. The big killer for linear regression is basically interactions. Which interactions you should introduce? And there's so many possibilities, right? And think about an example. Still remember the Titanic story? In the Titanic story, did we talk about Titanic? Yeah. Okay. Titanic story, the main interaction we were talking about was like there's a sex variable, male, female. There's an age variable, adult, child, right? We say we want to introduce a dummy variable for sex, measure the difference between left and right. We introduce a dummy variable for age, measure the difference between up and down. But that's not enough. And we add a interaction of age and sex that basically captured the extra thing there. Okay? So the whole point there was the child effect for male and for female might not be the same. Right? That was what we're trying to say. Think about if you do that with a tree, what you see. Right? You want to allocate people in terms of their survival probability. Right? So when you have a tree, you may get first, let's look at age. Let me do that arbitrary. Right? Sex is easy. Male, more likely to die. Female goes right. Right? Then you do age, child, adult. Then you can do age again, adult, child. Right? So easily we have 4 leaves corresponding to the 4 cells. Okay? We have the male adult, male child, female child. And there will be 4 leaves here. And for the 4 leaves, you get different probabilities. Right? You can say male adult dies for sure. Male child, 0.6. Female adult, 0.5. Female child, 1. Right? Then you get different things. And this really easily captures the difference with a male child and female child. This is a male child. This is a female child. And they're different. Right? They're intrinsically different because they're on different branches. Right? And you don't need to do all these things because if they're different, they will figure out. Right? And alternatively, if you say, actually the regression says this interaction term is insignificant, there was actually no difference. Right? What would be the corresponding? If there's no difference among child, then the tree would look like you first think about age, adult, child, how the child survives. Then among adults, you talk about sex, male, female. You have a 0, you have 0.5, something like that, right? If there's no difference, then you will split your data in a different way, right? So you don't need to really worry about all these variables, are they interacting with each other? So the sequential structure automatically builds the interaction in there. The child on this branch and the child on that branch are different, and that's the interaction, right? So that's a nice thing. No more interactions. So we don't. So in that sense, when you are building a tree model, you don't need to think about anything. You just need to say, this is my y, these are the x. You don't need to think about any transformations, log transformations, polynomial transformations, interactions, all those things. You no longer need to worry about that, because all the others are basically nonlinearity. It would capture the nonlinearity natively. And the last thing, there's one more thing. The next thing is handling missing data, right? In regression, we say if you have a big table, one of the data points, one of the variable is missing, you have to take out that whole row, that whole point, because it doesn't work in the algorithm of regression. Regression requires all the data to be there, so you have to delete all the points with a missing data. So you can think about one data point. You have 100 variables, only one is missing. Now you have to delete that whole row, and you lose a lot of information there. Yeah? So tree can handle missing data in a pretty passive way. There are all kinds of way to deal with missing data, but the most straightforward and simple way is say, now I need to split passengers on Titanic based on their gender, but one guy, we don't know what was his gender. That's missing. So we just put it arbitrarily anywhere. We don't need to ignore that point. We just put it arbitrarily anywhere. Then next stage, we need to split by age. We actually know that's a child. Right? We can put that child down there, because every time when you're splitting, you just look at one of the x. Right? If that x is missing, it just pass that data point to the next stage. It would just go somewhere. Right? So there's a more complicated way of dealing with that. But the bottom line is, at least the algorithm will not break if you have some data missing. Right?
So there's no difference if you have a child, male or female, in terms of the effectiveness of the splitting?
You mean missing data doesn't have any impact?
Yeah.
No, that's not my point. Since you randomly put it there, you're subject to some errors, definitely. But at least you can run that. It's not. You don't need to worry about that.
You will find which is the best way to play it.
You never know, right? There's a missing, right? Think about that. If gender is missing, what can you do? You can do an imputation, put a majority there. But is that better than randomly put it anywhere? Right? It's not necessary. Yeah. But the point is, if you have a big row of data, a lot of predictors, if one or two are missing, you don't lose a lot. You can still use the other information. Right? That's important. At least you get your algorithm running. And actually, there was a beautiful application of this thing is imputation. Say, at this stage, the gender is missing. You don't know where to go. But you are basically allocating randomly that guy to this group. And you can actually check things there. This guy is in that group. In that group, how many male, how many female? You can put some imputation based on the fact that this guy is a child. Right? So there's some kind of a heuristic way of filling in the blanks based on the neighbors, the other people in that group. Right? So yeah, next week we'll talk about the random forest, and random forest has a application that's basically using this idea to fill in missing data, because eventually you put people in a group, and yeah. So that's more accurate than the overall average. Overall, there are 60% of male, 40% of female, and now, but in this group of child, there are less male, more female, right? So this is more accurate in that sense. Okay, so these are the important things, and next time we'll talk about more advanced tools that actually keeps the good things about trees, get rid of the bad things, right? So we have talked about the bad things, mostly about accuracy. Accuracy is bad because of there's only a finite number of leaves. Right? You have a question? No? Okay. So because of the leaves is small, so accuracy cannot be good. But the main killer is this guy. Tree is highly variable. you have 200 data points, you build a tree, you get something like that. You take out your 2 data points, you build another tree, it can fundamentally different. And the sequence of all these things becomes reversed. So you were talking about a big story about years of how important is years of experience. The critical threshold is 4.5. But once you get another data point, you run it again, the whole story no longer exists. That's an issue. Although you can easily interpret a given tree, but that story doesn't last very long. It's very dangerous. In the past we used this tree to do customer segmentation. So there's kind of a retailer kind of a thing. They have some data about their customers. He said, I want to group my customers according to their spending. And then you tell me what are the commonality of the customer in different groups. So we did a tree, something like that. But whenever we have new data coming in, we do this again, things become fundamentally different. So it's very frustrating. And the other signal of that is, like earlier when doing the slides, my optimal tree is having 3 leaves, the baseball data set. Later when I run the code in the afternoon, I don't know what's wrong. I got 4 leaves in the cross value. I don't know. Maybe I changed the seed or something like that. But they're not very consistent. Also, we talk about the computational issues already, right? That's one of them. But the main thing is about variability. Okay? So let's stop here, have a break, then we talk about the coding. 不准，所以它的 prediction 都不错。对，所以呢，你想的3个例，还有 n 种方式达到3个例，达到相似的 prediction， 所以到底用哪个就。一般就是这个，我给你讲了3个点。
然后我们做 prediction 的时候，就是看这个新的这条反高用哪个，然后再就用那个 mean。对。然后还有这个刚才你讲 classification error， 不读这个字节结构。
So we have 3 illustrations, but the first 2 are mainly reproducing what we have in the slide. It's not too much. So we start with the regression one, regression trees. Well, this is the baseball data. Like I just said, hopefully the result is consistent with what we have. We have used this data several times, right? So there's not much. I'm plotting the data out. So that's the first picture we have seen in the slides. So then we can do the tree. One thing is there are at least 5 or 6 packages in R that do decision trees. And they all have various more simpler or more advanced kind of a fix to all these algorithms. I'm showing you the most basic, the simplest one, because I don't buy those improvements anyway. So it doesn't solve any of the problem. So let's just use the simple one, just understand the simplicity. So this is a tree. And tree is a nice function. If you check the help, it's pretty much the same as the LM or GLM we have been doing. So you just need to specify the formula and data. Right? That's a nice thing. If you check the help later when we do, this is regression, so you don't need to do a lot of things. Later when we do classification, you can choose Gini index, use Gini to do the split, or instead using deviance, so that there's a choice here. And the other thing is, earlier there was a question, if there's a missing data, what to do? So there's an NA action is NA pass. Not sure what are other possibilities. See, the default is whenever there's a missing data, do nothing, dropping them down the tree as far as possible, right? So that's the default. And if you don't like that, you can specify your own functions to handle the missing data, right? Filling in some means, you can write a function to do that, but that's not the point here. And the main thing specific to trees is this tree control. Later we'll talk about tree controls. That's when do you stop building the trees. Right? That's a terminating conditions. So for now, let's just use the default. So the default, now I can run that. I'm using my log salary as y, years and hits as x. So the tree we got, if you just check the object, this is the verbal description of the trees. You have some information about the leaves, branches, all these things, right? So in particular, what are the important things? So you start from the root. Right, so those are the column names. This is the node index, number 1. That's the root. Name is root. There's no split. 263 is n. That's how many data points that are going through this node. Right? Everybody, 263 data points. This is a deviance. So that in the regression problem, this is a residual sum of square. If you just stop here, that's the error. Everybody in one big group. That's the y value. That's the mean for this whole group. Overall average. Okay. Then the root was split into node 2 and 3. Right. Years less than 4.5. Years larger than 4.5. Right. So earlier we said if we can split that, I will talk about the deviance later, but in the first branch, we have 19 data points. The other one, we have 173, right? So that's a split. Then on the left-hand side, this is the deviance on the left-hand side. So this is the error. After splitting, we obtain this mean for this left group, and the error for this 90 points is this much. That's the deviance for the left group. And for the right group, we have the mean salary being 6.3, and that's the deviance for the right group. So the total deviance at this stage is the sum of the two groups, right? So that's 72 plus 42. That's 114, something like that. And so the length of that branch earlier we were talking about was the difference between the original deviance, 207, minus the total deviance after splitting, 114. Right? So that's about 90. 90. So that's the length. Yes.
What do we use log?
We don't need to use log. Yeah, I don't know why I use log. We don't. Doesn't make any sense to do that. You don't need to do that. But tree might be different. The tree might be different. But yeah, anyway, that's just the deviance. And the length of that first branch is about 90. When plots the trees, all the length of the branch are proportional to this reduction in deviance in a relative sense, right? Then we have the further split number 4, number 5 by years. Then we have number 6, number 7 by hits. Then we have some further splits. So at the end, all those splits marked by a star are the leaves. So we have 8 leaves in this tree. Right? Yeah. In practice, we don't read all this information unless you want to pull out some of the numbers for your further analysis. Right? But in general, we don't really read this. You can do a summary. The summary is like the summary in linear regression. You see how many nodes are there in the trees, what's the total deviance at the end, and divide by the sort of a degree of freedom. So that's the average deviance, or average residual, or that thing. Right? Then there's a bunch of information inside the tree object. Yeah, let's not struggle with that. In particular, there's a frame thing. That is, if you want to pull out the exact information about the trees at any stage, any level of the trees, you can do the trees.$frame. So that gives you a data frame kind of structure, so you can easily get all the information you need. And there's also an interesting one called where. Where basically tells you, for each of the data points, eventually which leaves they end up staying in. Right? So that's all these players, they're staying in particular leaves. You can do a table that shows you the distributions. Right? There are 8 leaves indexed by these numbers, and within each leaf, how many data points are there. You can see the smallest one is 5, so I guess the mean cut is, our mean thing is 5, right? The smallest possible number. All right. Most of the time, we don't do all these parts. Whenever we build a tree, we just do the plot. Right? So that's the most straightforward way of seeing what you have. Right? So that's if you do plot tree, you see something like this. You just draw the lines proportional to the deviance reduction, but it doesn't have the labels. If you want the labels, you need to do the text tree. So it add the labels onto that. These things are package specific. So for this particular package, you need to have 2 lines to do that. Some other packages give you a much nicer plot of the trees. But the informations are there. Right? So that's the 8-leaf tree we have been talking about in the slide. Another good handy function for visualizing trees is the so-called partition tree function. So it just maps the groups into the two-dimensional predictor space, right? So you can quickly visualize what's going on. So this is so-called partition dot tree, but it's nice, but it only works with 1 or 2-dimensional, right? When you have more than 2x, that doesn't work. It doesn't know how to draw the 3D thing. And this guy can be overlaid onto your data points, so you can have a nice visualization like that, right? I somehow spent quite some time on that. You can see there's a long kind of a string of commands basically trying to color the points in some weird way. There's a formula to determine the colors. But ignore the colors. If you don't need the colors, this is just a standard plot of the points. And so next, let's try to control the tree size. Right? This is inside the function called the tree control. Tree control, as we have said, tree control takes 4 inputs. The first one is the number of data points in your data set. It's a bit strange. I don't know why they need you to key in that thing. It should be easily obtainable. The other 3 are the 3 parameters you need to set. Mean cut is the minimum leaf size. Any children after split must be at least 5 points. Mean size is the parent. If the parent is below 10, you cannot split that further. Minimum deviance, this is 0.01. So you can see these numbers are super arbitrary. 0.01 deviance, kind of really data dependent, right? This is an arbitrary thing. So in general, you should check these things and set your own numbers. What I'm illustrating here is I'm building another tree 2, using the same formula, same data, but changing the tree control to mean size to be 2, mean deviance to be 0. So mean deviance is set to 0. That means I want to split all the way to the end. But the other conditions are still there. Mean size to be 2. So the minimum leaf are 2. So if you plot that, you have this massive, a lot of tiny branches. And don't even try to add the labels. That doesn't. Yeah? But you can see there are a lot of tiny improvements over deviance, right? Okay. So that's about the building part. Next is pruning. Prune has a function called prune.tree, so you can just do prune. I'm pruning the previous tree with 8 leaves here. So prune is a pretty complicated function. In particular, earlier we have said when we prune, we should we recommend people to use misclassification error to do the pruning. But you can also use deviance. There's no particular theoretical foundation for that choice. But the important thing is really the new data. When you prune the trees, the ideal setup is you have some data from out of the sample, right? Like when we do cross-validation, you have the one chunk of data being validation data. We should use that to measure the error and choose how to prune. And here, we just don't specify that new data. That means we are using training data to do the pruning. So this is the in-sample. Okay? This is not the right way of doing things, but let me just show you. Remember, the original tree has 8. What? Original tree has 8 leaves. If you just say prune this guy for me, it will try different sizes from 8 all the way to 1, right? And it will measure, basically there are 8 different models, different tree models. It will just shrink the tree step by step and end up having 8 different trees. And then it measures the deviance, basically the error. But since here we are doing in-sample, these are the in-sample error. When we do in-sample error, the optimal tree is always the largest tree, right? This is the in-sample. So it doesn't make too much sense to do this, just to show you can. Default method is deviance. Let's give you the deviance residual sum of square in this case. What else? There's a k. This k is the alpha guy on the slides. That has a one-to-one correspondence to the size. I just said that this thing doesn't make too much sense. Let's not worry about that. So you just need to focus on the tree size. That's good enough. And after you prune that, you can plot it out. Not plot. This is the deviance, how deviance changes over tree size, right? Because this is in sample, that's always decreasing. It's not surprising. So that's also not what we do in practice. The first step, important thing is the first step, build a big tree. We have already done. We have 8 leaves out there, right? The second step is the CV cross-validation, right? Just like a CV GLM, we have a CV.tree. Does that in one shot, one line. You can check the CV.tree a little bit. This guy is like the CV GLM net. It takes a tree object, run a cross-validation, and pruning that to the smaller versions and measure the cross-validation error instead of the in-sample error. Right? The default is tenfold, so you don't need to do anything. A beautiful thing is this rent. This is just like in CVGLMNet, we have the fold ID. So you can partition your data first and specify this is my partitioning, do your cross-validation using this particular partitioning. This is the same thing, but it's just a different name. So let's just run the default one first. This is a cross-validation, so we set some seed just for reproducibility. We just say CV tree, that's it. It basically reproduced the pruning part, and the only difference is the error now is a cross-validation error instead of a training error. Right? Now you can see which one is smallest. This is, again, number 4. So the optimal tree size is 4 in here. And you can plot the error as a function of the tree size. 4 is the best. Right? And the next one, I'm illustrating the idea of let's partition the data first. This is our old way of generating the tenfold partition. We have done that many times, right? So in order to compare different models on the same cross-validation partition, so we can just specify the rent is, let's use this particular partition. Right? And you do that again, you get the same answer. Right? That's not very different. And if you're curious, you can check the source code of CV.tree. Internally, the code is very short, if you check. Internally, if rand is missing, you can see if you don't really specify your rand, it does the random partitioning the same way. I think I copied the code from this. No, not this one. This is the bad way. Is that the bad way of? This is the bad way of splitting the data in balanced way. Right? So for each data point is sample 1 allocation group number from 1 to 10. Right? I think this is the bad way. Where did I get the good way? Don't remember. But if you check the code, it's not very complicated. There's some random partitioning, then there's a cross-validation loop from 1 to the number of folds. And in each loop, you build a model without a particular chunk. Then you prune. So this is the prune part. Then you prune using the new data. Here, that's the new data. So when you're pruning, you use the validation data, particular chunk I, and prune that to a particular tree size. Right? That's then calculate the error. So that's not very complicated, actually. What's this? Okay, I'm plotting the CV error. So this is CV error we have obtained for different tree size. And also we have the in-sample error earlier by the in-sample way of pruning. So that's the red line. Right? Just plotting these two errors together, just to show you don't use in-sample. Then after the cross-validation, we need to pull out the optimal tree size. So where do we get the optimal tree size? If you check the output earlier, tree1.cv, the optimal tree size, where am I? The optimal tree size is, first we need to find out which model minimizes the deviance, right? This is my index. It says number 5. Model number 5 here minimize the deviance. Then what's the corresponding K? What's corresponding size? I don't need K here. What's the corresponding size? The corresponding size is the tree size of model 5, right? That's basically what I'm doing. So that's 4, right? 4 leaves. That's this guy. So that's the second step. Cross-validation one line and choose the optimal tree size that minimizes the cross-validation error. Now we move on to the final step, prune the original tree. So we need to use, again, the same prune tree function. Take the original big tree and choose the best size. Best size is 4. So we just say prune this guy. And what we have is a tree with 4 leaves. Right? So that's not exactly the one on the slides. I don't know why. Last year I ran this 3 leaves. I don't know why. Maybe the software was changed. Alternatively, so you can prune the tree according to the tree size. You can also prune the tree according to the optimal alpha. Let's forget about that. Delete that. So with the final tree, we can plot it out. There are different ways of plotting. I'm doing a manual way using ggplot, or using an automatic way using the partition tree. So I'm just plotting the tree one pruned directly. So that's the final model. Okay? Any questions? Okay. So we're done with the baseball data. Next one, let's look at the tree demo. I'm showing you how to play with the tree control parameters. So this is the sine curve we have been talking about in the slides. So this is a sine curve. This is 100 data points we simulated from the sine curve. Now we do a tree to fit y over x, right? So we just do a quick tree. It says the optimal number of leaves is 7. So earlier we have the 7. No, let's not have the text. No, you need the text. So there's only one x, so I'm splitting everywhere according to the same x, right? But I have a different threshold. So if you plot the things out, that's the partition tree function again. Right? Earlier, the partition tree can plot a 2-dimensional thing. It can also do a 1-dimensional. Automatically give you the step function. So that's how to visualize a 1-dimensional tree. This guy has 7 leaves. So I have done the first step. I need to prune it a little bit. So I'm doing CV tree on tree 1. Somehow CV tree says the optimal is this guy. So the optimal tree size is 7. So this is an underfitting situation. You started out with a big tree with 7 leaves. After doing cross-validation, it says 7 is the best. Right? Probably this is there's some overfitting. And so I don't need to do any pruning, but I still have the same code. I know the best size is 7, so I'm not pruning anything. So here I have the code to plot the original tree and the pruned tree. They're the same. So now the question is, we have done the whole process, but the pruned tree is the same as the before, so there's something missing. Right? So probably we should build a bigger tree at the very beginning. So I have multiple trees I built in the following. There's a tree 2. So I'm changing the tree control. I want to show you the difference in different tree control parameter. So I have 100 data points here, right? So the first one, I set the mean size to be 50. What does that mean? I have 2. If this mean cut, I have 2. Cut is the size for the children, right? I have 100 data points, if I want to cut, I can only have at least 50 on the children, right? So if I do that, I have 2 nodes. Two nodes. And how many data points on each? 50-50. So if you force me to have at least 50 points on each children, that's the best I can do. Right? That's 50-50. That's not going to be a good tree. But now I'm reducing this because I want a tree that is deep, right? So I should reduce the size. So I'm making that to 25. I'm having 7 leaves. That's probably what I have before. And I make it to 20. I have 8 leaves. Not enough. I make it to 10. I have 16 leaves. Let's see what 16 leaves look like. 3, 5. Yeah. 3, 5 is already getting really crazy. A lot of things. Right? Anyway, earlier we talked about if we set that to 0, mean size to be 2, mean cut to be 1, what we will get is a 99. We have 100 data points, right? And 99 terminal nodes. I actually wanted 100, but yeah. So let's visualize. This is the original. This is the tree with 2 nodes. Right? That's 50-50. You don't really have a choice. The 100 points, you have to do that 50-50. So you don't even have a choice. This is how many? 7. Not clear. Let me plot. This is the one with 8 nodes. This is the one with 16 nodes. So you can arbitrarily getting really close to the F. How about the last guy? Remember this plot? Somewhere we have done some similar things. Right? So this is basically every point in its own leaf. Right? So you have a perfect fit. 0 errors. What's the error for tree 6? Tree 6 has almost 0 errors. There's one guy is somewhere, I cannot find that point. But there's some error. Yeah. Okay, so you can basically play with this tree control to control the size. Then you can do the pruning again. Right. All right. So that's regression stuff. Next, let's do classification. Classification is the same data as your homework, the heart disease data set. So the same, oops, let me clean up. What? My data is gone? Let me clean the data. The issue for this heart data set is there are a lot of categorical variables. And and the Y is categorical. So the heart disease is roughly 50-50, so it's relatively safe for us to use classification error. Right? So it's not very unbalanced. And yeah, just like in the homework, we split the data. We save something for as a test data for later. So we do the trees, and the building part is the same. There's nothing to worry about. Y is AHD. All the others are X. So we are only using the training data. So there's a subset, right? There's nothing special. There's a big tree. So the important thing is when we do classification, you can see the information is not 100% the same. We have 148 data points on the root, and that's the deviance. What's the Y? That's the deviance. What's the Y value? So that's the majority vote. So among this whole data set, the majority is a no. So the Y label is no. So that's the classification for people in that group, right? Then follow that you have the probability. You can see these two numbers are probability. They sum up to 1. And one is for no, one is for yes. And I guess it's alphabetical because this is categorical variables, right? AHD, there's no, there's a yes. So in that order. So the first is a probability for no. The other is probability for yes. Right? If you want the probability, you can pull out the probability. So at the end, after all the splitting, you will see some of the leaves. For example, these are 2 leaves, right? Depending on the collateral larger than some number or smaller than some number, you have 5 data points on the left and 6 data points on the right. And you have some deviance, and the group label are no's. Both are no's. So you can have a split into 2 groups. Both are no's. Right? That's fine. But they're fundamentally different in terms of their probabilities. Right? They become 2 groups because they have very different probabilities. One group has 100% no's. So all the 6 patients are no's. The other group has 60-40. Right? So both, although in both groups the majorities are no, but their probabilities are fundamentally different. Right? So later when we do prediction, we want to pull out these probabilities. Right? We're predicting heart disease. We'll pull out the probability of yes. Right? We're using these things. So that's a quick note. When we have classification, we both have the majority vote and probabilities hidden there. So take a summary. This is the first time we have a regression. We have a tree with a lot of predictors. So you can see they actually highlight only 8 of the predictors were used in the trees. There's some others who were not used probably. And then the number of nodes, the deviance at the end, and misclassification error. Right? That's everything you would want. These are in-sample measures on the training data. Right? Not so important. So you can plot and add a text label. We didn't really explain how the software label the categorical variables. Think about at the root level, the first split is based on this thing. What's that? THAL. What's that THAL? Where's THAL? Here. So THAL is a categorical variable with 3 categories: fixed, normal, and reversible. Right? No idea what that, but there are 3 categories. So you, at the time of splitting, you need to specify which category go left, which categories go right. So here there's a simplified label says B. B means the second category go left, right? The rest go right. Okay? So normal is on the left. So that's the default way of labeling the trees. If you don't like this B's, like there's another one here. There's a BD. Can you see here? So this is for chest pain. Chest pain is here. Chest pain has 4 categories. It's BD is the second, and the fourth goes left, and the rest go right. Right? So this is a BD. If you don't like that, you can turn off the pretty option. So by default, this is supposed to be pretty. So you can turn off the pretty function. You'll get the original labels. Normal. Normal was the second one, right? Normal was the B there. And chest pain, you cannot see that. That's why it's not pretty. The second one and the fourth one, yeah, it's hard to see. Some of the categories can be huge, right? There's a better one called the pretty equal to true. If you do that, you will get some shorthand, short name for the categories instead of A, B, C, D. So N stands for normal, presumably. Chest pain. What was the chest pain? Chest pain, you see N, 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 and T. T is typical. N, N, N supposed to be the second guy. It's pretty smart how to get the N, N, N out there. Yeah. Anyway, so there's different ways of plotting the trees, but that's not the point here. So that's a big tree. We need to do the pruning. We do the CV. Now you need to be careful. So there's a difference. When we do pruning, we need to specify misclassification, right? Well, what's the point? I know. 9:30, right? You just said. Prepare what?
Will you be finishing soon?
Not sure. I'm okay. I'm okay. If they can hear me, that's fine. Okay. I'll try to be quick. Yeah. So that's a misclassification, right? So let's just do that. The issue is you can see the method is misclassification, but on the measures is still deviance. This is not really deviance. It's the misclassified points. Right? So how many errors you made with all these different trees. The trees started with 14, right? 14 leaves. 14 leaves, right? So it tries to be smart and choose some different size, right? I don't know how to force them to try all the different sizes, but yeah, no idea why is that. It's very hard to control that. So in here, what you can choose is the 6, right? 6 leaf is the best, okay? With the minimum misclassification error. So you can see the plot. You can choose the optimal size and prune the original tree. Use the optimal size. Again, whenever you're pruning, misclassification error. So back to 6. So that's the final tree with 6 leaves, right? Earlier we have no. Earlier we have those kind of a no splits, right? I have explained that part. But after the pruning, that's kind of a cleaned up. So you have no, yes, no, yeah, separate, right? So you can make a lot of nice stories about what kind of people are having high chance of a heart attack and all these things, right? Anyway, one thing we didn't mention earlier was a prediction. Now we have a tree, a final tree pruned, calibrated. So we need to do prediction. So it's pretty similar to earlier. We have a predict function for trees. The only thing you need to worry, whenever you do prediction, you need to check the type. Right? Remember earlier we have a type equal to response for GLM. Here you need to read the documentation a little bit. It has all these types. So a vector is the probabilities, like I chose vector here. It gives you the probability. Later you will see. Tree, I have no idea. You can go back and try. You can also get the labels. That's a class of each point, yes or no, right? And a more interesting one is where. You can predict on the data points it tells you which group it belongs to. That's a where kind of thing, right? Here we need a probability. So I just pull out the probability. And if you check the probability, that's just like earlier we have seen for each node, there's some probability, no and yes, right? One column is redundant. So later we will work with the second column, the probability of yes. So that's what we care about, right? And once we have the predicted probability, we can do the usual stuff, ROC, AUC, all the stuff, right? So we go back to the usual stuff. The point of doing this thing here is to compare with your homework. So last time you do the homework using lasso logistic regression on exactly the same point, same problem, right? So we pull out the second column, the probability of yes, using the test data, and we have the what? This is the test error for misclassification. It's about 20. The best is about 22, 23%. Right? It's worse than our lasso model, for sure. I also have a AUC value, was 79. Right? Last time the lasso was like 89, right? 88, 89, right? So it's clearly worse than those things. Right? That's their limitations. Okay, getting dark. Okay. Okay, let me stop here. And again, the important thing is this is the tool that captures nonlinearity in a nice way, right? So next week we'll talk about two other things, the random forest and the boosting. So by then we will cover all the three major ideas in this whole area. Last time the regularization is one big idea. Your tools tend to overfit. We regularize, make it smaller. We have talked about the pruning, that's regularization. And next time we'll talk about another idea that's in the random forest. That's basically observed the issue here. Trees tend to be overfit, and the overfit issue is driven by a lot of variance. The trees are highly variable, but they capture the pattern pretty nicely, right? So this is a low bias, high variance tool. On average, they're bad, right? But it's low bias, high variance. And the idea of controlling variance, one way is by pruning, regularization. The other way is by averaging, right? If we have a bunch of trees, then we can take an average over all these bunch of trees. They all have nice bias, and the variance average out, right? That's a kind of an ideal situation. So when we talk about the random forest, it's basically build a big forest, a bunch of trees in parallel, and we take an average. So we get rid of the variance. And the question is, how do you get a bunch of trees? You only have one data set. How do you get a bunch of trees? We'll talk about that next. So that's the second idea. By averaging multiple overfitted models together, you cancel out their variance, and the average is a good solution. Right? That's a second big idea. The third big idea is about boosting. It's also built on top of trees. The forest idea is building many overfitted models in parallel. They're independent of each other, then you average. The boosting idea is building many trees sequentially. That's the more powerful idea. It says when we do that in parallel, we want many trees. We want them to overfit to have smaller bias. We don't care about the variance because eventually they will cancel out. So we build huge trees when we do random forest. So we don't really do pruning. We just build a massive trees and many massive trees and average. So we want them to have a low bias. And the boosting idea is exactly the opposite. That's the fun part of that. Boosting says, I want to have really stupid trees, mostly with one split. That tree captures some of the pattern, at least it captures something in my data. Then it has a lot of a bad residue, a lot of errors out there, right? Then I'll build another tree to explain what are the errors. Do you see the point? I have one smaller tree. It's a fit. It has the residuals. And build another tree to explain the residuals. And build another tree to explain the residuals of the residuals. So eventually you have 10,000 those stupid trees, but each actually improve on top of the previous ones slightly. Then you aggregate over this 10,000 stupid trees, and that's going to be super accurate. And that's the other idea of fixing the errors by another model. So they built on top of each other. So that's the three major ideas in this whole area. Next time we'll do that. And random forest and boosting will be the top models in all kinds of predictions. Boosting is always the best, and random forest is always the second. But there's some trade-off, and that's why both kind of exist. Right? That's an overview of what we're going to do. Okay? Run.